Now we want to look at solving a constrained optimization problem. So here's the problem we want to look at. We want to choose a value of x and a value of y to maximize or minimize, as the case may be, z, which is some function of x and y. And that function is equal to minus 1/2 x squared plus 2xy plus 6x plus 3/2 y squared minus 8y, subject to the condition or the constraint that x plus y must equal 8. So how do we solve this type of problem? Well, we want to choose a critical value of x, a critical value of y, to maximize z subject to the constraint being satisfied. So we need to set up the Lagrangian that corresponds to this problem. How do we set that up? The Lagrangian will be a function of lambda, that new variable called the Lagrange multiplier that we introduce into this problem. And we treat it as a choice variable just like x and y. So our Lagrangian is going to be a function of lambda, x, and y. And the way we set it up is we rewrite the objective function, just minus 1/2 x squared plus 2xy plus 6x plus 3/2 y squared minus 8y, plus, then we write lambda, and then we write out our constraint, putting the constant first, and then we minus or subtract the constraint function x plus y. So it'll be minus x minus y. Now we need to get the first order necessary conditions for our Lagrangian. We want to solve for the critical values of lambda, x, and y that lead to a stationary value of the Lagrangian. And when we do that, those critical values of x and y, those same critical values of x and y, will lead to a stationary value of our objective function or a stationary value of z, subject to the constraint being satisfied. So let's do that right now. Let's get the first order necessary conditions for our Lagrangian. And here's what they're going to look like. We need to take the partials, find all the first order partials of our Lagrangian with respect to our choice variables lambda, x, and y, and set them all to 0, just like we did in chapter 11. So we take the partial of the Lagrangian, first with respect to lambda, and then again, to be complete here, that partial derivative is going to be a function of lambda, x, and y, the same variables, and in the same order that they appeared in the Lagrangian. And what will that be equal to? The partial of the Lagrangian with respect to lambda is just the coefficient of lambda, which is that expression in the brackets in the Lagrangian. So that's going to be 8 minus x minus y, and we set that equal to 0. We're also going to have the partial of the Lagrangian with respect to the next choice variable x, and it will also be a function of the same variables that the Lagrangian was a function of. And that comes out to be minus x plus 2y plus 6 minus lambda equals 0. Then we need to take the partial of the Lagrangian with respect to y. It'll be a function of lambda, x, and y. And once we find it, we need to set it to 0 as well. The partial of the Lagrangian with respect to y is equal to 2x plus 3y minus 8 minus lambda, and we need to set that to 0 as well. Now we have here a system of 3 simultaneous equations, and we have to solve them for lambda, x, and y. And there's many different ways we could do this. We could put it in matrices and use Cramer's rule. But a common way of solving the system of equations for this type of problem is to take the 3 equations, reduce it to 2 equations and 2 unknowns. So what I want to do is take those last 2 first order necessary conditions and try to eliminate lambda and reduce that to 1 equation containing the variables x and y, combine that with the first order necessary condition, and then we'll have 2 equations in x and y that we can easily solve. So somehow we have to take those last 2 first order necessary conditions and eliminate lambda. Well, one easy way of doing this is moving the lambda in both equations to the right side of the equality, and we have a plus lambda in both equations on the right side of the equal sign. And since they're both equal to lambda, we can set those two expressions equal to one another, and we'll get the following result. We'll get minus x plus 2y plus 6, which is this expression right there, equal to 2x plus 3y minus 8, that expression right there, and we've eliminated lambda. So now we want to reduce this equation and maybe just solve for either x or for y in terms of the other variable, and then maybe substitute it into the first order necessary condition, and then just get one equation and one unknown that we can solve for. So here's what we're going to do. Let's see, what if we subtract 2y from both sides? So we'll subtract 2y here, subtract from the right side, and we're left with a y over here. And then I want to move all the x terms over to the left. So let's subtract 2x from both sides. So this becomes a minus 3x over here. And let's add 8 to both sides. So we get a plus 14 over here. And this is the equation we're left with. So basically, I now have taken this 3-equation system and I've reduced it to 2 equations and 2 unknowns containing x and y. So now I'm just going to take this second equation, where I solve for y in terms of x, and substitute it into the first equation, and then I'll get one equation and one unknown, the variable x. So when I do that, we get the following result. 8 minus x is equal to y when I move that y over to the other side, and that y is just minus 3x plus 14. So let's see, to solve for x, let's add 3x to both sides. So what we get, this cancels to 0, and the 3x over here, 3x minus 1x is just 2x, and then subtract 8 from both sides, so 14 minus 8 is 6, so our critical value of x is equal to 3. And how do we get our critical value of y? We could go to either of our 2 equations in our system of equations and just plug in x naught and solve for y, whichever one is easier to work with. It looks like if we go to our first order necessary condition, remember that was 8 minus x equals y, and we already know that x naught is equal to 3, so performing that substitution, y is equal to 8 minus 3, or it's equal to 5. We could also solve for lambda, and to do that, we could just go back to our first order necessary conditions and take either of those last 2 first order necessary conditions. And since we move lambda over to the right side, we can solve for lambda in terms of x and y. So let's do that. Let's take our second first order necessary condition, which is lambda is equal to minus x plus 2y plus 6. And so lambda is equal to minus x, or minus 3, plus 2y, y was equal to 5, so that's plus 10, plus 6. So in this case, lambda is equal to 16 minus 3, or 13. Now the next question is, once we have our critical values of x, y, and lambda, we could put that into the Lagrangian and find a stationary value of the Lagrangian for our problem. And we could take that critical value of x and y and put it back into our objective function and get a stationary value of z, subject to the constraint being satisfied. So the question is this: once we solve that critical value of x and y that leads to a stationary value of z, subject to the constraint being satisfied, is that stationary value of z a maximum or a minimum over the constraint? Well, to determine that, we have to look at second order sufficient conditions. So let's turn to those right now. To see if we have maximized or minimized z subject to the constraint being satisfied, we need to look at the bordered Hessian for our Lagrangian. And how do we get the elements of this bordered Hessian? The elements will be second order partials of the Lagrangian, but they have to be arranged in a very special order. How do we find that order? Well, if we're very careful on how we did our first order necessary conditions, the order of our second order partials of the Lagrangian will be easy to get. So let's form that bordered Hessian right now. The first row elements will be L lambda lambda, L lambda x, L lambda y. So let's just write those: L lambda lambda, L lambda x and L lambda y. How do we get the second row elements? Go to, again, our second first-order necessary condition, and in order, we get the second-order partials of the Lagrangian Lx lambda, Lxx, and Lxy. So we have Lx lambda, Lxx, and Lxy. And for the third row, again, we go to our third first-order necessary condition and get our second-order partials of the Lagrangian Ly lambda, Lyx, and Lyy. So we're going to have Ly lambda, Lyx, and Lyy. Okay, now all we have to do is fill in those elements. So let's see what they come out to be. So again, if we go to our first order necessary conditions from the Lagrangian, L lambda lambda. Here's L lambda before we set it to 0. There's partial Lagrangian, partial lambda. And there's no lambda in there, so L lambda lambda is going to be 0. L lambda x, the partial of L lambda, which is, again, this expression before we set it to 0. The partial of L lambda with respect to x is just -1, the coefficient of x. L lambda y, the partial of L lambda with respect to y is the coefficient of y, which is -1. Lx lambda, go to Lx, the first order partial of the Lagrangian with respect to x, Lx, before we set it to 0. What's Lx lambda? -1, the coefficient of lambda. Lxx, the coefficient of x, which is -1. Lxy, the coefficient of y, which is 2. Ly lambda, -1, the coefficient of lambda. Lyx, 2. And Lyy, which is 3. And if you evaluate this third order determinant using the Laplace technique, you'll find that this determinant, this bordered Hessian determinant, comes out to be 2, which is positive. Now, what we have shown is that we can determine the sign of the second order differential of the Lagrangian subject to dy equal -gx over gy dx, but it'll be the opposite sign of the bordered Hessian. So this will be negative subject to movement along the constraint, dy equal -gx over gy dx. And if that condition holds, this implies we have maximized the Lagrangian, and this subject to this constraint. And in particular, for our problem, what we're interested in, we have a max of z, or a max of our objective function, f of xy, subject to the constraint being satisfied.